Okay, it says we're going. Streams live, streams good on YouTube even, on all of the platforms, so I'll just get started. Hi everybody, welcome back to our Astro Coffee Hangout. My name is Tony Darnell, and I run deepastronomy.space, and we've got a great topic to talk about today. We've got a good story to tell, because we've got with us some astronomers who were using citizen science. Now, you've all heard of Zooniverse and some of the things that they can do. Well, they've got another, I think it's brand new, but I'll have them tell us more about it, called Exoplanet Explorers. And they were using this new system in a really cool way. I just love this story. When I read the press release, it was all about this was being broadcast live, I guess, on a show called Stargazing Live, which I think is in Australia. So I want to hear this story. I reported on it in SFN 221, so after the hangout, you can definitely go check that out. But anyway, but today we're going to talk about the fact that those citizen scientists had found 5 worlds around a system known as K2-138. Now, K2 is the rebooted Kepler mission. The Kepler Space Telescope has been rebooted, and they call it K2. We've talked about that many times, what they're doing with K2, but this is the 138th system, I think, that was found by that. So let me bring up my my guests, my panel here. And hi, everybody. It's good to see you.
Hello.
It's good. We can see and hear you. Let me start by introducing my co-host. Dr. Carol Christian is from the Center for Emerging Media, and she has helped organize this hangout. So welcome back, Carol, and introduce our hangout.
Okay. Yeah, it's great to see you, and I'm really grateful that Jessie and Ian could join us to tell us about this project, their research, and also the citizen science work, because I am a fan of citizen science. I've had a couple projects with citizen scientists, and I really enjoy working with them. So many of you know that the Hangouts are sponsored by the American Astronomical Society and the American Astronautical Society for the astronomers and the engineers. And we are thankful for their support. And as you know, again, or for you newcomers, this is an informal discussion, and we just kind of have a roundtable discussion of the research and field questions and think of some ideas and talk about this particular topic that Ian and Jessie have been working on.
That's
so
right.
Thanks.
Yeah, this is your chance to be a professional astronomer for 1 hour, because we're going to get together and we're going to drink some coffee, or in my case, iced tea, in my Hubble Space Telescope glass, and we're going to discuss astronomy like they do in the real world. Hey guys, so my guest today, I have 2 really cool people here to talk about what they're doing. Dr. Jessie Christiansen, she is from CalTech. She is she's a staff scientist there. Let me put up her little lower third. This is much easier. I could make you big, but I'd rather, it keeps my button pushing down if I just put your lower third down there. So that's Jessie. She's in the upper left. Hi Jessie, welcome to our hangout.
Hi everybody, thank you so much for having me.
And you can follow her at Aussie Astronomer, is that right?
That's
on Twitter? Right. Okay, cool. And also joining me is Dr. Ian Crossfield. He's an assistant professor at the Massachusetts Institute of Technology. Hi, Ian. Welcome, and thank you for joining us.
Thanks for the opportunity.
Okay, well, let's get to the story. This is a really great story. Oh, wait a minute. Chatting time. Chat with us. This is live. This is interacting time. You can join us in a couple of ways. I'm on the live chat on YouTube. And I'm also live on Twitch. We're also live on Periscope, and we're also live on what's the other one? Oh, Facebook. So I've got those various platforms up, and I'm looking at the comments there. But, and folks, I can't emphasize this enough. If you really, I'm looking at this right here. This is the Discord chat, okay, for Deep Astronomy. It is awesome. Please go on it. The link is in the description box of this video. Go on there. Uncle Bill's there. Adam's there. Peter Q is there from Newcastle. And all these guys, we're building community, guys, and I'm looking here first, so please join us here. It would be really great if you could. You're supporting Deep Astronomy by doing this kind of thing, and by helping out on the Discord server. And so that's how you can ask questions and comments. But I am looking at all these other things too, because I don't want to miss out. I mean, I know you guys don't want to necessarily go over to the Discord. Okay, K2-138 was found in a really cool way. Now, who wants to tell me this story? Should it be Jessie or Ian? Because well, my favorite thing was you guys did this live on TV, didn't you?
That's right.
There's a show down in Australia.
So it's originally a BBC show, actually, called Stargazing Live. And they decided to do a traveling version of the show, and they went to Australia.
And said, hey, guys, let's find some exoplanets live. Right?
Yeah, so Ian had the idea to start Exoplanet Explorers, which is the citizen science project hosted by Zooniverse.
And the link to that is also in the description box, folks. So check it out.
Go do that. Go find planets.
Yes.
So it was actually only like a week or two after we started it, Ian, that they reached out to us and asked us if they could feature it on their show, right?
That's right. The timing was pretty serendipitous, but it worked out in the end, I think.
Right.
I'm sorry, but that took some guts because you got a live TV show and you're just saying you guys just launched this citizen science initiative. They're going to I thought I had problems going live.
Yeah, it was a little bit more than we had bargained for. We just thought we were slowly ramping up this nice, steady project. But then all of a sudden, the TV broadcasting channel for an entire continent is calling for us to help out with their project.
All right, so I want to get more to what Exoplanet Explorers does a little bit later on in the podcast. But let's go ahead. So you got called by Stargazing Live, and you were using this to I guess let's go ahead and talk about what Exoplanet Explorers does, because we kind of need that before we go further, don't we? What is the software platform set up to do, and what's the interface like? Is that an Ian question?
Sure.
Okay.
So the project really drew a lot of inspiration from the Planet Hunters project, which was also on Zooniverse. They worked with the original Kepler mission, helping citizen scientists find new planets. So we built off of their success to try similar sort of thing, but using the K2 mission, which is now surveying the ecliptic plane, as your viewers have heard many times.
Yes.
So it was just the motivation to try and both engage the public and also look for things that our own team's analyses might have missed, because we know we always miss something or other. And that indeed we did. And one of the new things we had missed that the citizen scientists found was K2-138.
So this is because, and the reason projects under the Zooniverse banner work so well, and Carol, you've got experience with it too, is that there are just some things that automatic image processing doesn't catch, right? You need a human being to look at all of these images, right? Is that why these things are set up the way they are?
Yeah, I mean, pattern recognition is definitely part of it. The human brain is wired to be able to find patterns in things. It's a survival mechanism. But it's not just the human brain. It's also just the sheer number of observations that are coming in every few months from the spacecraft. We just basically were getting way behind and getting through things. So it was like, you know what? There's this huge crowd of people out there who want to help us. Let's just give them the data and see what they find.
Now, I don't want to put you on the spot, Jessie, but do you have a rough idea how much data comes down from K2? If you don't, that's fine. It's a lot, right? It's like gigabytes.
So it's about 100 million new observations every 3 months.
100? Now, when you mean an observation, do you mean an image, or do you mean a
So that is about 10 to 20,000 stars get observed something like, now I'm going to have to do the math in my head. It's 30-minute cadence. It's 1,500 a month. So it's 10 to 20,000 stars get observed 1,500 times.
Okay.
So multiply those together, and that's how many observations we have to sift through looking for the little dips that are caused by planets.
That's right, and that's important. You need a time series. You can't just take one picture of the sky and then move on. You've got to be looking in that area, get a lot of buildup to get those little dips as the planet moves. So, okay, so we've gotten behind. I'm sure that if you had enough computers, enough supercomputers, or maybe you had something like what they've got at the supercomputing center in Illinois or something like that, can you do this work, or is it just something you really can't get enough computers at? You need people.
These days, of course, machine learning and deep learning and AIs are all the rage, and I think there's a lot of untapped potential there for making a lot of strides in all sorts of branches of astrophysics, including transit searches. But at least at the current day, there's still something for humans to contribute. And
yeah, well, I can tell you now, and I don't mean this in any disrespect to any of you guys, but I've worked with astronomers for 30 years. I've seen how they write code, okay? And if they're writing... if they're writing any AI code, I'll be shocked. I mean, it's all.
I just wanted to interject a historical perspective, because I think it's interesting to note our guests are too young to even know anything about this. But there is a book called The Glass Universe, and it talks about how imagery was done on glass plates to keep the film, because the emulsion had to be stable, and so film wouldn't work. So on glass plates, and many women had to examine those plates and classify what they saw. And that's the kind of astronomy that went on. And first there were visual observations through a telescope where you wrote down what you saw. So slowly we've evolved to the case where we develop algorithms, but those algorithms come from our heads trying to duplicate what we do. So it always starts with us looking at the stuff and saying, oh, I wonder if I can make an algorithm that does the same thing I do. But the great thing about citizen science is lots of people look at the data and can analyze it, but lots of people are thinking in a different way than maybe the science team is. So they might discover a new way of looking at the data that the team didn't think of. And we found that in the citizen science project that we did. So it's actually a really interesting thing to do, because you learn a lot about your own science when you do it.
Yeah.
Yeah, well, it's an interesting point, because so we're really fixated on finding exoplanets. That's what Ian and I really like to do, because we want to learn more about them. But then when you throw all this data out to the citizen scientists, you get all this like, but what's this star doing? And what's that star doing? And what does this mean? And you're like, oh yeah, there's all this other cool stuff happening. It's just, we want the exoplanet.
Well, yeah, that's how the Yannis Vorwerp was found, I believe, in another one too. It was done that same way. This new thing, nobody.
Right, the green piece.
Yeah. So, all right. Well, let's talk about the discovery itself. So you've got this citizen science platform, Exoplanet Explorers, and people go there and they are categorizing what they see in there. Presumably you guys are, I haven't gone on and seen the interface, but presumably you guys are going in, you are presented with pictures of things, and you tell the computer what you think it is. How was K2-138 found? How was it? First of all, you said it was missed by all of the other automated techniques, and yet it was found here.
So I'm not sure if it's strictly true to say it was missed. We hadn't really gone through this data set yet. It was a brand new data set.
Okay, you just hadn't been processed.
We just hadn't found it yet.
Sure.
So what happened was, so the TV show went for 3 nights. So it was 1 hour per night for 3 nights. On the first night, the project got introduced, amongst other astronomy topics as well, but the project got introduced and people were encouraged to get online and start classifying and looking for
The show was telling people, go out and do this.
Yeah, exactly. Yeah. So we went from a few hundred users with a few thousand classifications in the first couple of weeks when we were just ramping up to, in the 48 hours between the first hour of the show and the last hour of the show, we had 2 million classifications by 10,000 people. So that was as Ian said, we were just like swamped. So we wanted to announce something really exciting on the show, though, that the citizen scientists had found. So, of course, the producers of the show really wanted us to sift through and find a habitable planet. And it was like, well, actually, those are really, really hard to find. That's why we don't have a lot of them.
We need more than just a light curve to see if it's habitable or not, right?
Well, yeah. So that was exactly what my thought was. Like, what can we do if we just have a light curve? And so I thought that we should look for a signal, a star that had multiple planets going around it. Because if you only have one planet going around a star, that can be maybe a big star and a little star, or some other kinds of false positives. There are other things that can explain one regular dip around a star. But if you have multiple regular dips around the star of different periods and different depths, really the only thing that we know of to explain that is a planetary system. So I actually have the Slack channel where I'm in there like, why don't we look for a multi-planet system? And Gert, who's one of the co-authors, is like, that's a great idea. I'm going to go make a cup of tea. And then 10 minutes later, he comes back in and I've gone through and I'm like, here, they found a 4-planet system. It had 4 at the time, and now we know it has 5. But like within 10 minutes, it was like, there it is. They found it.
Okay, so in the time it took this guy, Garrett, who couldn't make it today, to go get a cup of tea, the citizen science had found 4.
Well, so they had been classifying all of the signals, and so we just had this huge text file basically of classifications, and I was like, okay, I'm going to go through all these and see if the same star has multiple classifications around it, basically. And so that actually was a fairly straightforward search, and almost immediately I found a new one where different people had found each of the different planets. So it was really exciting. And they didn't realize as they were doing it, because they just get presented with one planet signal.
Sure.
But I could see looking at the data that there were 4 around one star.
Okay.
Wow, that's fantastic.
I love that story. I just love
Yeah.
it. I mean, it's like you can't even script it any better than that. So I'm looking at the press release, and it was like some of them there was like 2 or 3 of them had already had 90 classifications or 90%. I can't find the text on it.
One of the real strengths of citizen science, which is something I'm really excited by, besides the like individual systems which are exciting, is the statistics you get out. So if we try to answer the questions of how common planets are, then having a huge crowd of people help us go through the data gives us a really complete sample. So one of the things we required was that 10 people vote on each signal. So when I say each of the planets were found, they were each found by at least 10 people. So we required at least 90%, so 9 out of the 10, to say, yes, it looks like a planet.
Okay.
So 3 of the 4 had 10 out of 10 or 100%, and 1 of the 4 had 9 out of 10.
Okay, yeah, that's what. I found that here. So that was your first multi-planet system that was ever found, I guess, by using this crowdsourcing technique. So that worked really great. So let's talk a little bit about the system then. I mean, let me pull this up. Let me get rid of this. So I have a graphic that you provided, Jessie, of the K2-138 system. It shows, well, you want to talk about it a little bit?
Sure. So the citizen scientists, when we launched the original project, found 4 planets. So on this graphic, the 4 planets that they found were C, D, E, and F. So we were really excited, and they announced on TV. And then Ian looks at the periods of those 4 planets and says, wait, you guys realize this is a chain, right? A chain of resonances. And what that means is the periods of the different planets are related to each other. So for every 3 times C orbits its planet, D goes around twice. And then for every 3 times D orbits its planet, E goes around twice. And then for every 3 times E orbits its star, sorry, I've been saying planet, orbits its star, F goes around twice. So it's this chain of resonances. And then we had another colleague working on the project with another citizen scientist, and they realized that there on that same chain was another planet inside the 4 planets that we'd found, which was smaller, so the signal was shallower, so we didn't see it immediately. And that's B now. So now there's 5 planets, at least 5 planets.
And what kind of star is K2-138?
So it's an early K star, so that's a little bit cooler and a little bit yellow or oranger than our sun. A little bit smaller, a little bit cooler, but not like an M dwarf, like a little red one.
So it's kind of nice, and it's kind of a nice little star, like it's very not too unlike ours. And these planets, what do we know besides their relative sizes? Can we get any sense of whether they're rocky or not, or are they? These look like pretty. So I mean, they're like really super Earths. Are they super Earths or? Yeah,
so the periods, which aren't listed on here, are very short. So you say it's a nice star, it's true, but these planets are all super close to the star. So this inner planet B, I'm like pointing at my screen, like you can see me pointing.
Yeah, all they can see is the graphic right now.
This inner planet B, it goes around the star every 2.3 days. So the inner planet is about 1300 Kelvin. So this is not a nice place to be around this star, even if it's a nice star. It's really hot. And then then the periods are like 3.5 days, 5 days, 8 days, 12 days. So it's basically like a Fibonacci sequence. It's really cool. And the outer period is 12.8 days. So the temperature out there, I think, is like 800 Kelvin. It's still really toasty. All of these planets are way too hot.
Yes.
So
in terms of sizes, B is the only one that might be rocky. It's about 1.6 times the size of the Earth, and that's about where we think planets transition from being mostly rocky to having like rich layers of volatiles and waters and ices and gases. So it's right on the cusp. We can't say yet. The other planets, C, D, E, and F, are all sub-Neptune, we call them. So they're between 2 to 3 times the size of the Earth, and we don't think they're rocky. We think they're predominantly these other volatiles and gases and ices.
Okay, well, Adam is asking on Discord, will this planetary system be amenable to radial velocity observations? So our audience pretty much knows what radial velocity and the transit method are. So
Well, that's an excellent question.
Yeah.
So so my team that Ian and I are on have access to the Keck telescope. And when we started looking at the star, it was a bit too spicy for our blood, which means like the star itself had a little bit too much going on. Stars themselves can be quite active and noisy, and those kinds of noise signals can dwarf radial velocity signals, which would be how you'd measure the masses. So we tried, and we were like, we don't think we want to spend all of the resources on this. But I actually found out after I published the paper that a group in Europe using the HARPS telescope, which is another very high precision.
HARPS is on ESO's telescope, right? Yeah.
Yeah. So we found out that they've actually been studying the system quite intensely. So they have over 100 measurements, and I'm really excited to see their results when they publish masses, because it'll be really exciting to have the masses of these systems.
Yeah.
Of
Okay.
these planets.
And yes, because that is the difference. Radial velocity gives you a good idea of the sizes and the orbital periods of these planets, but the radial velocity gives you more information on the mass of the planet itself. So
transits gives you sizes, radial velocity gives you mass, and then together you have density. And then you can answer the question of whether they're rocky.
Yes. Good. All right. That's very good. So one plot's commenting, worked on this, but just started too late to catch the system. Well, it must have been an exciting time for the people. Did they know, by the way, the people working on the website, that this was going on, that they were on TV, or at least
Yeah, so they certainly, most of them did. As Jessie said, when the project started out, it was just a few dozens or maybe 100 people at most. Then as soon as the TV show started, it jumped to about 10,000 participants. So we infer from that most of them knew about the show.
Is this show? I'm sorry, I'm very infatuated by this show, because I wish there was something like that here in the States.
Absolutely.
Is it still going on in Australia? Or is it a BBC in England, or what show?
So the show is a BBC show. They are doing another one right now, not right like today, but somewhere in the next month or two, I think March, they're doing another. They do it annually. It's an annual.
I see. It's a once-a-year thing.
So they're doing it coming up in March, and I think they're doing a citizen science project again, but not exoplanets this time.
Ah, okay.
Certainly a niche in this country that's open to be exploited, I think.
Oh, no kidding. What a great show that would be. Okay.
Yeah, so besides the citizen science result, part of the show that I really loved was, they would cut to an astronomer sitting at a telescope and be like, well, what are you observing? And the astronomer would be like, I'm looking at Europa. And then the next night they would come back and be like, did you get your observation of Europa? Yes, and look, I can see methane in the, et cetera, et cetera. So it was just really like to be able to see astronomers doing live, results and observations, I think was really, the crowd really got into it. It was all positive feedback.
Oh, wow. That is a great idea. So it's similar to what we're doing here, Carol, right? I mean, we're trying to get astronomers talking about their research live and as soon as after they publish as possible. But that's like that takes it to a whole different level with.
That would be fun.
Yeah, that would be great to actually be at the telescope. And we should do that with Hubble, Carol. I mean, Hubble has this thing where on Twitter you can see what it's looking at any given time, and it tweets out. Carol helped set that up, where you can see what Hubble's looking at. It'd be great to go, hey, did you guys get that data? And the problem is it's all embargoed and nobody wants to talk about it for a year. Okay.
Well, I actually think that point is one of the most interesting things in terms of interacting with the citizen scientists. So we announced like almost immediately that this planet had been discovered, but the paper only came out last month, so 9 months later. So for the citizen scientists to understand like the pace of science, like the rigor that's involved, that we needed to go off and do all the statistical analysis and re-observe the star and make sure we understood it. And then when we found the fifth planet, go and derive those properties. And then write the paper. And then, all of the people who were super involved were like watching it go through the referee process. And then the paper gets reviewed and comes back and there are comments, and then it finally gets accepted, and then a press release. So they were involved, I think, in a way that they really appreciated the access to the scientists, but they also were like, wow, this really takes a long time.
Yeah, that's right. It does. It's got to be peer reviewed, and that whole process is it's good though that they were able to be a part of it in that way.
Yeah. So we have 5 citizen scientists, one for each of the 5 planets, actually as co-authors on the paper.
How did you pick though? I mean, how was that determined?
Well, so for the 4 original ones, I think it was the first people of the 10, each one. Well, the first person who used an actual name, because some people use like screen handles and stuff, which is less obvious use in, an authorship list for a paper. So the first people who used actual names for each of the 4 planets who voted on them.
Okay. Well, let's see. So Dragon President is asking about TESS. TESS is launching. hopefully soon. No earlier than March is what I last heard. Is TESS, when it gets up there, going to be helpful in further investigating what's been found so far?
So that's a great question. So I'm here at MIT right now, where
that's right.
The people who test together are finishing up their final reviews, and we're still hoping to launch the satellite in a bit over a month. TESS's mission, for any of your audience who doesn't know about it, will be to survey almost the entire sky for new transiting planets. So where most of the sky, it'll only look at it for 27 days or so. So that means it'll only pick out the very shortest period planets. So for any of the areas of the sky that K2 looked at, if TESS is to overlap any of those, that's actually the default plan is that it won't overlap. If it did, TESS wouldn't have a lot of anything new to add there beyond 30 days of additional baseline a year or two after K2 had looked at it for 80 days. So
nominally, it's not going to overlap K2 TESS.
Nominally, it's not, and that's partly just a function of design. K2, because of how as your audience knows, because of how it has to point, only looks at the ecliptic plane, whereas TESS's main goal is to actually it's actually looking most steadily at the outside of the ecliptic, so at the ecliptic poles, because that's where, if it finds interesting planets there, that's where the James Webb Space Telescope will be able to stare the longest to do any sort of follow-up atmospheric characterization, to not just learn sizes, masses, densities of the planets, but actually learn what might their atmospheres be made of in a detailed molecular sense.
Right, because JWST is going to have instruments on board specifically designed to help us understand these atmospheres of these exoplanets in ways that nothing else can right now. By the way, for those of you who don't know, and I'm sure most of you do, but I'll say it anyway, TESS stands for Transiting Exoplanet Survey Satellite, and it is going to image the entire sky over the course of its mission several times to build up looking for Earth-sized planets. There you go. There's the logo. I'm sure. Well, you're at MIT, so you and Sarah probably work very close together too. Sarah Seeger, correct? Yeah. So, yep. So anyway, Sarah Seeger is involved. Also, I've invited her to a hangout. We'll see if she comes at some point. But the JWST will. Well, actually, before I go there, I want to talk a little bit about the time cadence. These are. You're saying that the Exoplanet Explorers citizen science is looking at data throughout the Kepler or the K2 mission up to now. Can you explain the importance of why we've got to look at the same area of sky over and over again to gather up these measurements?
Sure.
Yeah.
I'll take that one. So the transit method relies on the fact that if a planetary system is lined up the right way, it'll block some of the starlight. Now, if you were an alien civilization looking at our sun and you were lined up the right way such that Earth transited, Earth would only transit once every 365 days for about 12 hours. And then you'd have to wait a year until it came back and transited again. Now, when we're trying to characterize planets, what we really want to see is 3 transits. Because if you only have 2 transits, it could be 2 similarly sized planets that just happen to go in front of the star, and it's not actually measuring their years. So we really want to see 3 transits, so you know that this is the year of the planet, and then you see it again. Yes, that's the year of the planet. So for things like the Kepler mission, the original Kepler mission, Kepler stared at a single patch of sky for 4 years because its goal was looking for planets like the Earth, and you needed to see at least 3 transits in order to catch it. So K2, because as your listeners know, can't do that anymore, it tiles the ecliptic in 80-day patches, which means that the types of planets that we're finding with K2 are different from the types of planets we're finding with Kepler. And they'll be different again from the types of planets we find with TESS, since TESS is doing the whole sky, but most of the sky only for 27 days.
And that's why, I guess it explains why this planet, all of the planets that you were able to find, I'm going to put this graphic up again, were so close to the star, because it happened to be in a time when you were seeing these planets that happen to transit often. This is biased, by the way, this technique, because we don't have long enough time series data to look for a really, really long period of time. You're going to miss anything. For example, how long has K2 been looking? About 3 years?
So K2 has been looking now for just under 4 years.
Okay.
The thing to remember is that unlike Kepler, K2 only looks at any given patch of the sky for 80 days each.
Right. So you've got that constraint plus the fact that it's only been doing this for a few years. If you've got a planet that's got I don't know, like Jupiter, right? You know, dozens, hundreds of years before it goes around the star. You're not going to see it. You're certainly not going to get 3 transits. So you're really...
So that's true. On the other hand, there's an interesting population of a very small number of stars in the original Kepler field that only show 1 transit each, and these transits are really slow. Normally, a transit lasts a few hours, but these things last many days, and so it's clear. And so over a period of 4 years, there was only a single transit. So we caught a handful of these with Kepler. It's just that because we only saw the 1 transit, we'll never really probably know how long their year actually is. But they're out there.
Right.
Right. And there are other planet finding techniques like the radial velocity technique or the direct imaging technique, which blocks the light from the star and looks for sources of light around the star that are more sensitive to the long period things. It's just that transits, as you say, is sensitive to short period things.
Sure. Okay. So I'm going to go ahead and I'm going to try this, guys. I'm going to put this. They've got a really cool animation. I'm going to turn off all my little business here, and I'm going to put this animation up. Okay, it should be playing now. No, wait, no, it's not. Now it's playing.
Oh, I see it. I see it playing.
Okay, do you? Okay.
Yes.
And there is music happening, or at least there is sound. We're talking over the sound. So explain what we're looking at here, Jessie.
Okay, so this is an animation produced by Matt Russo at System Sounds, and it's the 5 planets going around the star, and every time one of the planets transits, you hear a note, and the tone of that note, how high or low that note is related to its period. So the short period planet in the middle is the one that's going around like ping, 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 and then as you go further out, the planets are going more slowly, so the note gets lower and lower and lower. And the reason it actually sounds as nice as it does, given that you have 5 different notes playing at the same time, is because of the resonances that I was talking about before. The fact that the gaps between all of these orbits are this interval, this 3 to 2 interval, which in music is called a perfect fifth. So they're all perfect fifths apart, which is why it sounds so nice. It's a musical system.
Okay, and I'm going to play it. I'm going to try to play it one more time, and then we'll just let it play this time.
Okay. Oh, this time I don't see it.
Oh. Hang on, let me try one more time. There we go.
We're not seeing it.
Why isn't it going on? Oh,
I don't know. Can you see it?
Oh, no, I don't see it. Oh, well. I knew this would screw up. Oh, well. At least we got through it once before we had a problem. Okay, well, so is this publicly available, this animation? Can we make it available to people? Or
it is. So, and then the website that made this is system-sounds.com. They created this machinery to build this animation for the TRAPPIST-1 system, which is another very famous system of a compact system with a resonant chain of small planets. So Matt Russo, when he saw the press release, actually said he stayed up all night to just remake it for the K2-138 system because it was another, compact resonant chain, and he was like, it's going to sound fantastic, and it does.
I will, after this Hangout's over, guys, I will put a link up. Oh, Andrew Planet's already done it. Thank you, Andrew. Appreciate it. He's put a link in the chat there, so people can go and check it out. All right. Well, let's see. Looking at some of the Uncle Bill is commenting on Discord. Gotta love citizen science. Common thought is that the common man can't compete with big projects, but in truth, the sheer volume of data has enhanced the possibilities for hobbyists to contribute, and that's really true, isn't it? I mean, yes. I remember back when I was coming of age, the only thing I could actually participate that I could remember in was AVSO. Do you guys remember that? The American Association for Variable Star Observers. Sure, and what you could do is you could go through your telescope and you could look at variable stars and you could write down what you thought the magnitude was, and then you'd write it on a piece of paper, and then you would send it in and they would compile it.
So they're actually getting involved in test follow-up, AVSO.
Are they? Okay, good. Yeah.
Yes, because a lot of the targets will be observable.
Yeah.
Sorry, say again, Carol?
A lot of the targets will be observable. Actually, I worked on the test proposal, and I have my test cert.
Very good. Tess, Tess. Carol, you've worked on everything. It's amazing.
Yeah, we worked on the archive because we're going to support the archive like we do for Kepler.
Okay, Galaxy is commenting, wow, first time they're telling indications for exojupiters and Saturns in the Kepler data exist. Cool. let's see.
So I think there's a paper by Dan Foreman-Mackey that was published a year or two ago, which lists some of these very long period candidates.
Okay. Larry Keese is wondering, is there a way that he was wondering if, I guess he's very active in a lot of our hangouts, as well as the, I guess in citizen science. And he goes, he'd love to be able to contact Jessie and Ian, probably not possible. Is there, I could perhaps, Larry, if you email me and after I ask them permission, I might be able to give you some contact information.
Also through the wonders of the internet, anyone can find our contact information.
I'm sure. Yeah, I didn't want to offer it though.
whatever Larry has.
I did.
It couldn't be 10% as crazy as half of the emails we get from people out there. So between space mirrors and everyone who has found that Einstein is wrong, there's no shortage of interesting mail that we get to receive.
Absolutely.
Right. So so anybody, but definitely if you want to get involved, this is still running, right? The Exoplanet Explorers. It's
yeah,
still
just
up?
last month we put up 3 new campaigns of data. So a campaign is one of these 3-month chunks. So we uploaded another, I don't know, like 10,000 signals or something. So go look.
What's the time scale? Are you going to keep doing this for as long as there is data, or?
Yeah, so Exoplanet Explorers is specifically K2 data. K2 is currently finishing campaign 16 and is hoping to get through campaign 17, but there is a fuel issue, unfortunately, just because of the new configuration that the spacecraft has to operate in. It's using fuel faster than Kepler was. So it's actually going to run out of fuel sometime in the next few months. We're just trying to get every second we can out of it first. And then, so one of the things that's come up recently is, are we going to do something for TESS? So TESS is going to have an even larger problem with volume of data than K2 does, because it's doing all of the sky, and it's doing all of the sky every 30 minutes instead of just Kepler and K2 are doing tens of thousands of stars every 30 minutes. So it's going to be a big problem. Whether or not we turn Exoplanet Explorers into a test project or if we start something new, we've been talking with a lot of the other citizen science projects about doing some kind of combined effort instead of, splitting up the audience across 9 different but very similar projects.
And I talk to a lot of people in my vlogs about starting their career in astronomy. And folks, this is why I keep saying you don't need to go the actual astronomer with a capital A career route if you want to, and are interested in data processing, handling large amounts of data, programming, writing programs that would sift through and help find objects within the data. There is a booming market for that skill set. So if you want to work with data, that's huge. I mean, that would be a very highly in demand skill set. Wouldn't you guys say? I mean,
that's right. Big data and how to mine it efficiently is one of the big things.
Yeah.
I mean, your comment earlier about how astronomers write code, it equally applies to AI as big data. So we need actual computer scientists to help us with this, or we're just going to flounder around.
That's right. So look into it, folks. I'm telling you, you will get work if you can handle large amounts of data and sift through it, and be able to distinguish, whether something is a galaxy or a star, and even measuring these light curves. And what are we talking about? Dip. By the way, these dips are not big, are they? We are talking about what? Little teeny tiny. How much of a percent of a dip are we talking about here?
So for
Go ahead, Ian.
Yeah, I was just going to say, so for the K2-138 system, when we've been talking about the biggest dip was about 1 part in 1,000, 0.1%, and the shallowest one was something like 1/10 of that. So that's the original Kepler mission found a few planets with dips even smaller than that, but not too many. It just gets really tough to see them.
Well, I remember early on in the Kepler mission, there was something like measuring the light dip as a fly goes across a headlight or something like that. We're talking really tiny amounts of dips here. But Kepler was a high precision instrument, wasn't it? It was designed to find Earth-sized planets around stars, and that required an even more sensitive detector. What wavelength does it work at? I've always been curious. When it looks at these stars,
it's just broadband white optical.
It's just white light. Okay.
Yeah, so it's a very wide band pass, because you just want to get as many photons from the star as possible so that you can add them up and look for the dips. You don't want to cut it up into little wavelengths or anything. But that means that Kepler isn't a characterization instrument. It's just a detection instrument. And then you have to go and use something like Hubble or JWST to actually look at it in the different wavelengths and find out more about it.
Okay, now I cannot have. Oh, go ahead. You want to add something to that, Ian?
Well, I don't know, Jesse. I don't know if that's a natural segue into your next plans for this system.
Let's go for it.
Oh, yeah, sure. So there, one of the to tie this into the earlier conversation about sensitivity, there are hints that there's a sixth planet in the system. We see 2 transits that are separated by 42 days, so one near the start and one near the end of the K2 data. And like I was saying, you really want 3 transits. But the transits are so shallow, it's hard to do from the ground. So we've actually just recently been awarded time on the NASA Spitzer telescope, which operates at the infrared, not the optical, to go and, for one thing, search for the 3rd transit of this putative 6th planet. We can predict where it should be, so we have a window of time. But also we can measure it in a different waveband, so infrared instead of optical, and then start to learn something about its atmosphere. So fingers crossed we find it in about 5 weeks.
Great. All right. Well, that would be amazing.
Yeah, that's great.
I can never have an exoplanet hangout without Adam asking about exomoons. I really want someone to find some exomoons, please. Okay. So will you comment for Adam, who desperately wants to find an exomoon? What the challenges are in finding these are moons around planets that we've measured transits for.
Yeah, so I think all of us in the community would love to see some exomoon love out there. And people have been looking diligently ever since the Kepler satellite launched. It's going to be the best tool to find them, if we find them at all, for a long time to come.
I'm sorry, what is TESS?
Sorry, the Kepler.
Oh, Kepler. Okay.
Ever since Kepler launched. TESS doesn't have as long of a time baseline, and it's not as big of a telescope, so the precision won't be as high. So I think if Kepler didn't do it, probably TESS won't, but I'd love to be proved wrong.
But theoretically, Kepler or K2 is sensitive enough to find an exomoon?
Kepler has found a few. Jesse, what's the smallest planet Kepler found? Mars?
There's a Mercury-sized planet.
So if there were Mercury-sized moons out there, which is not too much bigger than our moon, technically Kepler could have seen it. The challenge is to see these small things, you really want to stack up a signal, seeing it several times. And because a moon is orbiting its planet as the planet orbits the star, it means every time you see the moon, it's not periodic. Sometimes it happens a little bit earlier. Sometimes it happens a little bit later. It's always confused and muddled in there with the bigger main transit of the planet itself. So
that would be a crazy light curve, wouldn't it? You'd have a signal embedded within a signal.
Right. So have you had David Kipping on one of your Hangouts?
I don't think so.
No.
Okay, so we have one exomoon candidate from Kepler data that he's following up with Hubble, he and his student. It is, if you actually look at it, they do have what they think is a crazy light curve. There's only 3 events, I think, but each of them, instead of seeing a nice, clear, symmetric transit from one body, there's some kind of asymmetry, which they're hoping is due to an exoplanet, and they've been following it up with Hubble to try and see if they can confirm it. I mean, an exomoon. You
hear that, Adam? You heard it here first. There's an exomoon candidate on the way. See? It pays to watch these Hangouts, guys. Thank you for that question, though, Adam. I do know you love your exomoons. I do know that. John Suffol's got a good question here. What percentage of systems show the same kind of resonance? You were talking about this resonance that this one had. Do you see that often?
No, actually, so there's this kind of an emerging class of systems. So we had been seeing that there were more and more systems with lots of small planets close in. So this is they were called STIPs, I think, because astronomers love terrible acronyms. It's like systems of tightly packed planets or something. So there was this new class of systems, all of these like small planets tucked really close in. And now that we have enough of a sample, we're starting to see a small number of those with these chains of resonances. So there was TRAPPIST-1, which has the 7 planets. There's K2-138, which has the 5, maybe 6 planets. And there's maybe 2 more systems that show these chains of resonances where you've got 3 or more planets that are all locked in to this dance with each other. So it's not a large number at all.
But TRAPPIST-1 was one of those systems.
That's right.
Wow. Okay.
So I can't remember the exact order, but it's in a sequence of resonances as well. They're not all 3 to 2. There's like an 8 to 5 and a 5 to 3 and a 4 to 3 and a 3 to 2. That's more of a grab bag of resonances.
Well, as a follow-up question to that, John's asking, and this is really a good one, in the sense that this is kind of hinting at how we found Neptune, I think. We knew it was there before we actually saw it. He's asking, and do these resonances give clues as to where other planets might be found further from the star? So you said you've had hints that there might be another. Do you get any information from these resonances on that?
So we did. Jesse, you just described that a little bit ago, right? That's how we identified the innermost planet, is that we saw these, I guess, the four C, D, E, and F planets all in these near 3-2 resonances. And then we thought, well, let's give it a try. And so we looked, what if we just extended the chain one link further in? And lo and behold, there was a transiting planet there too.
Okay. Ian, we're getting about 3:45, and I realize that you said you might have to leave. So at any time, if you have to go, I understand. Just go ahead and exit the meeting, and you might. I just wanted to announce that if you had to go, it's okay. Let's see. So, oh gosh, now we're off on exomoons. Okay, so now we one plot is asking. So now we started it. Now, people are so fickle, right? We know that now that we have it. We have so many exoplanets out there. There's one around every star at least. Probably 1.6, I think, is the average around every star. Now we're like, oh, well, exoplanets. Who cares about those? What about the moons? Have you seen any moons yet? So how many moons, this is from one plot, would you consider to be out there through Kepler material, based on the Kepler observations, based on the moons in our solar system? Or, I mean, what do you guys think? How many moons would you think are out there?
I mean, that's really hard to say, since at the moment we have exactly one candidate from Kepler data. I mean, we can always extrapolate from our solar system. And before we had Kepler or indeed the entire field of exoplanets, that's what we did. We started from the solar system and we were like, okay, when coming up with theories of planet formation, what can we do to make the solar system? So people designed all of their theories around making the solar system. And then when we went out there and actually found planets, we haven't found anything that looks like the solar system yet. Everything looks completely different. So I'd worry about extrapolating from the moons in our solar system, given that we haven't found anything like the solar system yet.
That's right. The thing we can say, I think, pretty confidently is that there aren't lots of Earth-sized moons out there. I think if there were, or moons, bigger than the Earth, if there were lots of those out there around other planets, those would be big enough to have seen around a decent number of systems. It could be that every planet has a moon like our moon, and I don't think we would know. Okay. I think that would be still consistent with the data. It's just the sensitivity isn't there. Finding things the size of Earth is right on the hairy edge of what Kepler accomplishes.
The thought that we could do that at all blows me away. I mean, that's true. Okay, so Andrew Planet is asking, so using the transit method, is it easier to find planets around small stars? Is it easier to find planets around small stars, especially large planets? So does the size of the star, is it easier to find them around small stars? Does it matter? Is the dip in brightness? The dip in brightness is what you care about. So, I don't know. Can you find more around small stars?
Yes.
So we're biased a little bit.
That's a duck out, Jesse, so thanks.
Sure. Bye,
okay,
Ian.
Thank you, Ian. Thank you very much.
Appreciate it.
So the depth
Thanks
of the
a lot.
dip is a ratio between the size of the planet and the size of the star squared. So you just take the size of the planet divided by the size of the star and square it, and that's the depth of the dip. So exactly it relates to the size of the star. So a very small star will give you a deeper depth for the same size planet. So if you think about Earth going in front of our star blocks 100 parts per million, but Earth going in front of an M dwarf blocks 1%. So suddenly that's a much more tractable measurement to make. The problem is M dwarfs are almost all pretty faint. So there's not a lot of really bright M dwarfs to study in the same way that we can study other stars. But that is definitely, the field has definitely moved towards concentrating on cool stars as where to find, especially habitable planets. Because it's not just that the depth is bigger, but the habitable zone is much closer to these stars. So if you imagine that, like, when you're on a beach and you're standing beside a roaring bonfire, you have to stand back. But then through the night, as the bonfire dies down, you huddle closer. So if you imagine planets around M dwarfs, they have to huddle a lot closer to be warm, which means that you see more transits.
Okay, good question. All right, Dragon.
Also, M stars have a little problem, is that they may have a lot of flares, and so it doesn't help with finding the transit if the stars brightening.
They have a lot more correlated noise, which can hide the transits.
And anyway, go ahead.
No, I was gonna go ahead and finish, Carol. I'm sorry, I didn't mean to.
Well, it could also compromise, even if you find something that you might call an Earth-like planet, it may compromise, formation of any kind of life.
Right. So it's not just
anyways.
the flares, right? It's also the UV flux that comes out of these M dwarfs is much higher than G stars.
They could be nasty places.
Yeah, and I just wanted to follow up with that too. Is just like, to me, that's another area of astronomy that's that's relatively brand new now, is measuring the activity on these stellar surfaces. That's something we really couldn't do before either. And I think they're seeing convective cells in some stars. They're looking at astroseismology. They're seeing the activity deep within the star. So this is an amazing time. We're getting a lot of information now. Dragon President is asking, and this is a little bit off topic, but it's related. Can you talk a bit about the recent detection of extragalactic exoplanets? I read last week, and I think we have all seen on the news that they've found the first planets around stars in another galaxy.
Yeah. So what they found was, so when material is falling onto a supermassive black hole at the center of a galaxy, it emits a lot of light, a ton of light. And then if there is something between us and that galaxy, any kind of massive object, it acts like a lens. It's like holding a magnifying glass over the background galaxy, so you can see in more detail the light that's being emitted. Now, for some time, we have known that the light that's coming out of these galaxies shows variations in specific elements, like iron, I think, is the one they measure in the paper. And so far, those variations have always been attributed to changes in the material falling onto the black hole, like differences in density, or if the disk has some substructure, that kind of thing. Because it's basically velocity variations, like what's happening is the line profile of the element is getting broadened in a specific way. So in this study, what they found was a much larger broadening than they had seen before, something like twice as big. And so they postulate that this could be caused by if that distant galaxy had a foreground population of free-floating planets that would introduce this broadening. So that's one interpretation of the data. I don't think it's the only interpretation, but it's an interesting one. It's exciting to put it out there.
Yeah. So the error bars are pretty big then.
Yeah, and I mean, there are other things we can explore, I think, to see what we can answer with the line broadening. Yeah,
that's kind of like Tabby Star. Remember that? It was like, what could be this Dyson sphere and all this, maybe comet swarms, and then it kind of got narrowed down a little bit.
It's always dust.
Yeah, it's always dust. Okay. Let's see. There was a question that just scrolled past. Where did it go? Let's see. With the Andy Tom, hi, welcome. With the capability of Kepler, do you think TESS or the JWST will be capable of detecting extragalactic exoplanets, while we're on the topic, with either radio spectroscopy or the transit method?
So, I don't think so. I mean, as I was just describing, this observation of this reputed exoplanet population was really a very, it was an observation of something completely different that just might have been affected by exoplanets. So by radial velocity or by transit, actually finding things in another galaxy is incredibly difficult. If you look at the amount of our galaxy that we've searched with transits and our RV, it's a tiny fraction. Like if this is the galaxy, we've looked at like this much of it.
All right.
We haven't even found things on the other side of our own galaxy yet. So I don't know if that's a point that is widely appreciated, but we've only searched the local few thousand parsecs around our sun.
That's amazing. Yeah, that is an important point. We've just started, folks, and we're already seeing some pretty amazing things. We haven't even seen our own galaxy. There's parts of it that are going to be always hidden to us, though, right? We're never going to be able to look at the other side, for example.
Right. So we'd have to infer properties of the other side from what we see around us.
Right. We can
assuming that we're not in a special place.
Right. So there's another question. I think it was from Achilles 308. Yes, and this is more on the resonant orbits idea, which is really interesting, by the way. Are resonant orbits more stable?
Yeah. So that's a really good question, and I'm going to use it to explain a little bit about our theories of planet formation. So,
well, that's good, because he's also asking, what does this teach us about planet formation? So
fantastic. I'll send you your check later. So we have these competing theories about planet formation. And the problem is where we see planets today, so like this tight set of planets very close to their star, we know that those planets can't have formed there. They must have formed somewhere else and then migrated in. And there's competing theories about how that migration happens. One is that the planets interact with each other very strongly and like kick each other out of the system and swap places. Like there's a model of our solar system that theorizes that Jupiter and Saturn swapped places at one point. And then you end up with a very kind of violent migration. And with that kind of thing, you can't end up with these resonances that you see. The other theory is that the planets all form in a disk of material, and before that disk of material gets eaten up by the planets, it works to slow the planets down, and they get kind of dragged into the star, and they get dragged in together. And when they get trapped in a resonance, then they get locked in resonance, and then they come in and they trap the next one, and then they come in and they trap the next one. And that might be how you end up with these chains of resonances because they are stable.
Wow, that's amazing. And that may be more common than we know, right? I mean, this could be a pretty... what's our solar system like? It's not very resonant, is it? I mean,
there are some resonances. So Pluto and Neptune are in a 3-to-2 resonance.
Okay.
The Galilean moons of Jupiter, there's a 4-to-2-to-1 resonance, and I'm going to forget which 3 of the 4 it is. I'm a bad astronomer, but 3 of the 4 Galilean moons are in a 4-to-2-to-1 resonance. So there are some resonances. With the asteroid belt and Mars and Jupiter, there are resonances. So it's not uncommon. But to have this actually like unbroken chain of like resonance, that's new and interesting and tells us something that we didn't know before.
Okay. Well, one plot is asking, will Exoplanet Explorers be fusing AI with citizen observations in the future? Will there be some kind of fusing, do you think?
That's not currently in the plans because that's not mine or Ian's expertise. Kepler has been, or people who are working on Kepler data have been working, for instance, at Google with the Google Brain. One of the recent discoveries that was announced out of Kepler was actually discovered by Google AI. So there are definitely AI projects and there are definitely citizen science projects. I don't know yet where that intersection will be.
Carol, what about you? Could I get you to maybe comment on that? You've worked with Google in the past. You've worked with the Zooniverse citizen science initiatives. Do you see that happening where maybe we're going to see some kind of merging of the citizen science and maybe some artificial AI stuff?
Well, initially when Zooniverse started, there was a group that were in machine learning and they were very interested in what was going to happen. I think they haven't been quite as engaged, but I think that there are some possibilities there where they could.
Who hasn't been engaged? The AI folks or the
AI or the machine learning people haven't been as they were initially. But I know there's still interest because in the Zooniverse world, that's why it's a verse. There are like these expert classifiers and how they do the expert classification is really interesting. So that's another whole part of when you have an expert classifier, what do they think about? What are they looking at? How do they know? And you have to understand that in order to inject that into the machine learning and the AI. So I think it has a lot of potential. And as I said, initially they were very engaged in it. And I'm just not familiar enough with the project as a whole to know how many of the AI people are involved. But there's definitely potential there.
Okay. Well, Achilles was also commenting, citizen science will teach the AI. It's clear. That's probably true. You're probably going to get some,
if I could, completely off topic, but there was a citizen science project that was actually not in Zooniverse, but it was about protein folding. And they had made these rules. The scientists had made this rule about how proteins could fold. And so then they went off and let the citizen science do it. And the humans found all different ways because they had no preconceptions about what proteins were supposed to do. And so they had to go back and retrofit their algorithms on how they thought proteins could fold, and that gave them some insight into mutations, for example. So you never know what you're going to get by using the brain power of a lot of people who maybe have not been trained in the discipline to think a certain way. So it's really very worthwhile. I think.
Yeah, I agree. And like one of my favorite things, I did one of the initial Galaxy Zoo things when it first started. And what's nice about it is they set up a very clear training program to get you into a mode where you're able to look for whatever it is they're asking you to look for. And like Jessie said, you want at least 10 people, I think you said 10, right? Looking at the same thing and confirming that they all saw what you think it was. So
Right.
yeah, so okay.
But in some of the instances, like in Mars and Moon, they're the ones who found the lava tubes from the data. You know,
Really?
so not even thinking about craters and impacts, they found the lava tubes.
That's
Like,
awesome.
now of course there are lava tubes.
All right. Well, we are out of time. It's 4 o'clock. I want to thank my guests today very much. Thank you, Dr. Jessie Christiansen. She's a staff scientist at CalTech. Also with us was Dr. Ian Crossfield. He's gone now, but he is a astronomer, also as assistant professor at MIT. Both of whom worked on this really interesting story. I love this story. So thank you guys for taking time out to talk with us about it.
My pleasure. Thank you. Thank everybody who takes part in these kinds of things to make it happen.
Yeah, and please, the link is in the description box. Go check it out for yourself. Get involved.
Go find planets.
Go find planets. That's right. And if you're still with me, most of you still are, thank you all for watching. Please support Deep Astronomy by liking this video. Click on something, share it. You're helping support Deep Astronomy by getting the word out that these things happen. So please do that for us. Don't forget to join our Discord chat, because as soon as I hit the stop broadcast button, this live chat's going away and everything you said in it is gone, but not in the Discord chat. So please join us on that as well. Thank you all so much. And next week, I think we're having our first Future in Space hangout with Harley. I've invited Sarah Seeger and Natalie Battaglia to give us an update on the test mission. They haven't responded yet, though, so I don't know if they will. But that is hopefully what's going to happen. Otherwise, we'll do something else about Future in Space. So thank you all so much. Thank you, guys. All right. Thank you all for watching.
Thank you so much, Jessie. Really appreciate it.
No worries. Thank you so much.
It was fantastic. All right.
Thank you all for watching, and as always,